we have a proposal that a given four-dimensional theory of super Yang-Mills should be dual to a superstring theory, a full theory of quantum gravity with gravity and quantum mechanics and so on in AdS 5 times S5. We did it by studying a system at low energy from 2 points of view, and both led to some description plus some 10-dimensional supergravity. So when we equate both, we cross out supergravity, and we conclude that what remains at low energy is, on the one hand, the low energy degrees of freedom of a stack of D3 branes, and that's just the massless modes, n equals 4 super Yang-Mills. On the other hand, everything in AdS 5 times S5, because everything is redshifted, and so everything that is inside this AdS 5 times S5 box looks like a low energy. And so we conclude that the full theory of quantum gravity in 10 dimensions is dual to a theory without gravity at all, just quantum mechanics in 4 dimensions. It's quite an amazing statement if you think about it, right? And the easiest theory is in less dimensions, it has no gravity and so on, right? It's not like everything looks more complicated on the right-hand side, right? We have more dimensions, we have quantum gravity, we have strings and so on, and that's dual to a theory that looks simpler in all possible aspects. There are no strings, there's no quantum gravity, it's just quantum mechanics. That's what makes AdS, that's one of the reasons why AdS CFT is such a powerful duality, because there are so many things we know about quantum field theories that we don't know about quantum gravity. And so we can say that this relation, to some extent, is our best definition of what quantum gravity means. So you would say quantum gravity is defined through this relation. And that's one way of thinking about AdS CFT. Okay, then if we follow the parameters in what we said, we saw that on the one hand, in n equals 4 super Yang-Mills, we have, for example, this 't Hooft coupling. On the other hand, the 't Hooft coupling, this G square n, was related to the size of AdS. Now, the size of AdS, if you remember, we found the AdS metric with this L there, which means that if I rescale my fields properly to really write my string action, where everything is dimensionless, as we always did in this lecture, taking the coupling outside, these powers of L will appear here. This would be L squared appearing here, right? And then everything here would be dimensionless. Do you agree? And therefore, this, you can say it's the string tension. It's what multiplies the string theory action. Or you can say it's the string tension measured in units of the string length, if you want to make it really a dimensionless quantity. And so lambda, this constant here very large, which is a string tension very large, is when string theory is perturbative. Remember that a big prefactor to the action means weak coupling. So string theory is perturbative, it's easy when lambda is very large. But of course, Yang-Mills is the exact opposite. Yang-Mills is perturbative when lambda is very small. So that means that easy things in gravity, where you deal with classical gravity and classical string theory plus corrections, are very hard in Yang-Mills and vice versa. So it's what is called, this thing is the key characteristic of what's called a weak/strong duality. It maps weak coupling to strong coupling and vice versa. Now, a duality is only useful if we have a dictionary, right? If I tell you that theory A is dual to theory B, this is useful if I know how to translate quantities in theory A to quantities in theory B. Otherwise, okay, it's nice to know that the things are dual, but it's not so useful. So the first entry in our dictionary, we could think, would be, let's try to study what's the simplest possible object I can study in this conformal field theory. Well, it would be the dimensions of operators, right? We saw they were the energies of quantum spin chains. Now, remember, what are these energies of quantum spin chains? They are the eigenvalues of dilatations. Do you agree? But dilatations in RD is equivalent to time translation in R times SD. That was one of the things we saw in the beginning, right? And so thinking about dimensions in a CFT, it's equivalent to thinking of energies of the same CFT in R times SD. They are the same, because the generator is the same. The generator that applies dilatation, it has some spectrum, but that's the same generator that applies translations when you go to the cylinder. Right? It's just exactly the same. And so we learn that in this cylinder, if this is time, the energies conjugated to this time are these energies that are the dimensions. Correct? But you remember, AdS is filling in this cylinder. It's saying there is time, but there is the inside as well. And inside this box, now I can have stuff like a string. And here a string is rotating, for example, and doing something. It's not doing very much in the sphere, this example that I chose. It's a string that's mostly rotating in the middle and doing very little in the sphere. And this string has this time, which is the same as that time. Remember that the boundary of AdS is flat space. And so this, they share the coordinates at the boundary. So this time is that time. Right? And so these energies of the string are conjugate to this time, that is the same. And so our entry in the dictionary would be that the energy in Young-Mills, which are the dimensions, are equal to the energies of the string. Do you want me to put energies of Young-Mills or dimensions? The same thing. Which one do you think is nicer to put here? Delta or E of Young-Mills? Delta. Okay. So the dimensions of the CFT in n equals 4 are equal to the energies of a string. So this would be an element of the duality. This set of numbers is equal to this set of numbers. And so this duality is hard. And so one thing that is useful, it's great to have checks of the duality. And so one obvious check is to take one state, psi, and compute the energy of that state psi in the gauge theory versus the state of the same state psi in the string theory, and check that they are the same. So we need to identify a given operator is a given string. You need to make sure that you identify it correctly, which operator is which string. Compute the energy in Young-Mills, compute the energy in the string, and try to compare. So this is what I'm going to try to say a few words in the second half of on the second part of the lecture. But in the first part, I want to make a few more comments about AdS CFT. So please, so I have until, I have 50 minutes more, right? Okay, can you remind me in half an hour? So in half an hour, I should definitely be doing that.
In half an hour, counting this way or counting the other way?
The usual time forward.
Okay.
In half an hour.
2.
Yeah, at 2. That's what in half an hour means, yeah. Okay, so in at 2, we must be trying to do a check of AdS CFT. Until 2, I think it's nice to make a few comments about, general comments about AdS CFT. Okay, so a couple of general comments. So one, we did this game of playing with some system and looking at it from 2 points of view. We took a stack of D3 branes and we said there is a low energy limit, and on the one hand it's Young-Mills there, on the other hand it's AdS5, and therefore I get a duality. So one thing you could say is, why not other D branes? Why not try other stuff? Why D3? Why not D5s? Why not D7s? Why not other stuff? And indeed, so that's an obvious thing. So we could try some other stuff. So none D3 branes, right? Anything else. Right? And indeed, there exists other AdS CFT dualities, some of which can be understood in similar way. So that's true. So that's important indeed. It's not special. It's not like the D3s was crucial or something. It was just one that was particularly nice. So typically what happens is that when you do this game with other examples, typically you get, normally what you get is either you get a very complicated AdS and a very simple CFT, or a very simple AdS theory and very complicated CFT. N equals 4, AdS 5 times 5 is kind of the equilibrium. Both theories are very interesting. And in most other examples, typically, one of the sides is much harder to study than the other. It's not the rule, but typically that's what happens. So the other examples would include some Chern-Simons matter theory in 3 dimensions. So it's Chern-Simons plus some matter. That's dual to type 2A strings in AdS 4 times CP3. Then there are some examples where you have, instead of 3D, you have 2D CFTs. That's much simpler. And those are dual to very complicated string theories here in AdS 3 times some compact manifolds. And they are kind of more subtle to understand. And then you have examples of higher dimensional here being dual to some theories that are quite mysterious there. But it's true that we could engineer with some other objects, and that is very important, and people do it all the time. Now, when we have an S5, we can Kaluza-Klein reduce, of course. We can reduce the S5, decompose just modes in S5 according to spherical harmonics in S5, and get an effective theory in AdS5, because S5 is compact, so I can Kaluza-Klein reduce. Of course, it's not a small S5, it's a big S5, so I need to take all the modes, but still, I can reduce, and I'm left with infinitely many modes in AdS5. And so, what we do is we get some kind of theory that for the quantum gravity, or no, for the quantum mechanics, seems to be related to 5D quantum gravity. And this 5 is, of course, 4 plus 1. So what's crucial is that we get quantum gravity in one more dimension. And this is what usually goes the name of holography. The fact that you have a theory of quantum gravity in one more dimensions. And how could it be that you have, how could we argue just from gravity that something like this holographic should exist? There are many arguments for this kind of thing, but there are all these black hole arguments. I believe you are having a course right now on holography more from this black hole point of view, right? Which you probably heard that if you have a system that the entropy that you can put in some region is smaller or equal than the area of that region, divided by 4. The argument being that if I have some system in some area, I can increase the entropy by throwing more books inside. But eventually I form a black hole. And the black hole has entropy. It's equal to the area divided by 4. And in the process, the entropy increased because I threw stuff inside. And so the maximum is the black hole. Right? So this came from a thought experiment of throwing books inside some region until I form a black hole. And therefore, we conclude that the amount of information inside the region is proportional at most to the area of that region. And that led people to believe that there should be some description of quantum gravity that only uses the surface and not the full volume. So somehow quantum gravity, all the information is incorporated already at the surface. Now that's very hand wavy, right? Someone tells you this, oh, try to find the theory, blah, blah, blah. Okay, but this is precise. So that's a precise realization of that hand wavy idea. Right? That there should be some way of describing gravity in one less dimension, etc. And so there should exist some kind of hologram that would come from these very hand wavy arguments. So AdS CFT is a precise realization of the holographic principle. There's something also nice that we got this 4-dimensional theory equal to 5-dimensional gravity. So here in this 5-dimensional gravity, there exists the graviton. In this 4-dimensional theory, there are gluons. And so this duality is saying that the graviton is made out of these gluons. There is a way of thinking of this graviton. If I think from n=4 Spring Mills, this theory that only has all these gluons and the superfield and the friends of the gluons and so on, they somehow describe the gravitons in the bulk inside AdS. And there is a theorem by Witten and Weinberg that says this is impossible. The theorem of Witten and Weinberg says that if I have a quantum field theory with a Poincare invariant stress tensor, there cannot be fields with spin bigger than 1 and non-zero momentum. So there cannot be particles that are made out of these gluons with spin 2 and higher. They could not be composite states. You could not construct them in they basically show that these two particle states would have some very weird behavior in the correlation functions.
Sorry, could you just say that one more time? Just the precise statement about the stress energy tensor.
Yeah, so a Poincare quantum field theory with Poincare invariant stress tensor forbids fields with spin bigger than 1 and momentum p mu, which would be integral of p mu 0 d dx not equal to 0. This is, yeah, so in a QFT, which is Poincare invariant, you could ask if you could construct some state that would be like the graviton, that would be some spin to state, and momentum k that would have some non-zero momentum k according to this. Okay? And the point is that if you were to construct it, you would be able to show that this state with t mu nu and with the same state again would have very weird properties, and therefore this state should not exist. And how do you avoid this in quantum gravity? In quantum gravity, this t, right, which is just delta S delta G is equal to 0. And so in quantum gravity, we have a theory of quantum gravity, we have gravitons. If you have a theory without quantum gravity, the claim is that you should not be able, in that space-time, to form massless spin 2 particles. So how could we do it? We did it because what happens is that there is an holographic direction appearing, and the gravitons don't live in the 4-dimensional space. The gravitons live in the 5-dimensional space. And that's how what avoids, that's fine. This does not violate Weinberg-Witten, since the graviton is in higher dimensions. And so that is not forbidden. The fact that you could have a theory where there is an emergent direction and then there are some massless modes in this 5 dimension, that's okay. That a priori was not excluded.
Can I ask one more question? Do you know if their theorem extends to a quantum field theory living on an AdS invariant background? Because you said Poincare specifically.
I mean, almost for sure it does, because locally everything is flat space, but I'm not positive. Okay. But probably yes. Now, another way of understanding this 5 dimensions is related to the way we motivated AdS to start with, right? So AdS appears naturally from an RG point of view. So remember, so the idea is that if you have the boundary of AdS, this Poincare space, this boundary is RD, and if you have points nearby each other, they propagate nearby. If you have points far away, they propagate well inside. But when you go far away to the infrared, you go well inside, and so it looks like this direction, Z, looks like some kind of RG direction. Right? You flow from the UV very close to the boundary, and then you come in and you are probing more and more IR physics. Now, if you had a theory that was invariant under RG, like a CFT, you could try to realize this by having a background that is invariant under dilatations. And that's precisely what AdS is. Right? AdS as a trivial RG, which you do by just having dx squared plus dz squared over z squared. This would be equivalent to having a trivial RG. Right? Things just translate trivially. And indeed, from this point of view, what we see is that actually from the point of view of just the symmetries of AdS, so the fact that we have the isometries, the symmetries of AdS, this implies something rather remarkable. It implies that if I take a quantum field theory, any theory inside AdS, and I can consider some correlation function here happening inside AdS, and then I can define a boundary theory, not through an AdS-CFT duality or anything, but starting with AdS and taking these points and dragging them to the boundary. Pushing these points to the boundary. That defines, this is a definition of some correlation function in the boundary where I have one point that's in position x1, one operator at position x2, and one at position x3 in RD. And this correlation function, because of the isometries of AdS, will transform like a CFT correlator. And so this will transform as a CFT correlator, just by definition. And so it implies that, for example, if you take it implies the following. It implies that you could take this operator here to generate a heavy particle, like we did in the lectures, right? And then this heavy particle will propagate and interact at some point. Now, heavy here means what? Well, it means that the mass of the particle times the AdS radius is much bigger than 1. Right? L is the scale by which anything in the metric changes. right? So it's a particle that sees locally flat space. Now, this quantity, ml, would correspond, according to the dictionary we just saw, to the dimensions of this operator in the CFT. This is the energy of my state, is the dimension of the operator. And so we will get a CFT correlator, but it's a fun CFT. It's a funny CFT where the deltas are huge. So you have very big deltas. You have 3 deltas that are very big because it takes these particles to be very massive. What do we expect for this CFT? Well, there should be the usual space-time dependence, and then a number, the 3-point function, right? Now, we can do 2 things. On the one hand, we can study this number using bootstrap, right? We learned in the tutorial, you saw how you could on the bootstrap put bounds on this number. In CFTs, given some external dimensions, put bounds on this number. You did it for very small dimensions, 1/8, right? But you could do for very big dimension. On the other hand, from a totally different point of view, we expect this number to be what? We expect this number to be given by some propagation of some geodesics till an optimal point, right? So we expect to be given by some geodesic factors, some geodesic contribution, right? This is what you computed by doing the saddle point of the 3 geodesics in another tutorial. Do you agree? Some function of the dimensions, right? Do you agree? So this is a particular function that you computed as a function of all these masses of these particles and the locations. You compute this. Times, when they meet, they see a very small region, they see flat space, times the coupling in flat space that couples particle 1, 2, and 3. How do I define a coupling of 3 particles in flat space, of 3 physical particles? I would define this coupling by saying that if I scatter 2 particles in flat space, I can have a pole in my S matrix, and this pole would have residue 1/p² minus the mass of my particle. And the residue is the coupling here. So if this is 1, 2, and this is particle 3, the residue here is G 1, 2, 3. And because there are 2 squared. Right? And so from this exercise, we would learn something fun, that we would have the couplings in quantum field theory. Any quantum field theory in D plus 1 dimension, they would be related to this C 1, 2, 3 in D dimensional CFT. Right? Any theory. I put a massive theory inside AdS. This should give me some. I should learn in this way about bounds on these couplings of massive particles in D plus 1 dimensional flat space from the bootstrap in CFTD. This is kind of something that I find really remarkable. So conformal field theories in D dimensions know about non-conformal generic quantum field theories in D plus 1 dimension. And in particular, we can ask now questions combining these 2 methods. We can ask questions such as, what's the maximum coupling in a quantum field theory between 2 physical particles? And we could compute it from the bootstrap, try to compute it directly in flat space and compare both. And that was the subject of your homework. Was exactly working this out in a simple case of an AdS2, which, as you see, combines various aspects of the various tutorials. I don't know if you had started to do this homework already, but that was something interesting. So any question here? Okay, so let's then write here a few more comments about now AdS CFT. This blackboard is not about AdS CFT. I would call this blackboard AdS. It will be CFT. It will be quantum field theory in AdS, implying a CFT at the boundary. There are no two theories. There is a theory I put in AdS that I want to learn about, and it creates an holographic theory. It creates a theory at the boundary, but it's not an independent theory. Right? So this, we should call it QFT in AdS, which contains flat space inside, because locally things are flat. So this contains flat. And instead of a duality, I should put an arrow and say CFT, conformal theory. Maybe I should not, I put an F, but I could cross it out because there's no field theory. There are no fields there. Right? I'm just going and defining my theory at the boundary like this. Yeah.
So to summarize the last board, you're saying that you can use like CFT tricks to constrain the coupling of the QFT, right?
Yeah.
So I know that there's constraints in the amplitude people that say like certain couplings just can't exist at all, like between certain types. Like I actually don't know them off the top of my head. Like maybe there's some pathological ones like high spin massless particles and gravity.
Mm-hmm.
How does that, like, how would that manifest practically if you were going to engineer that and try to rederive that on the CFT side? Is there a quick way to see, like, oh, this 3-point function would look like blah? Or...
Yeah, I don't know the answer off the top of my head. I would have to think more. Most of these exercises, we do them for scalar particles because it's simpler. That is exactly the kind of things we typically avoid dealing with spin. There are many indices, but probably there is a simple answer to that, but I cannot tell you right away. So AdS CFT. AdS CFT, there are many ways of thinking about it. So there are people that think of AdS CFT more generically, not that AdS CFT, but in general, a duality between a theory of gravity and a theory of quantum mechanics, as a definition of the gauge theory. That is, I say that I don't care much about the gauge theory. I mean, I care about the gauge theory, but I don't care much about how to get to the duality. But I will just trust the duality, and I will use the fact that it's a weak strong coupling duality to do easy things in gravity, like studying some black holes, some thermodynamics of black holes, something simple that we know how to do in gravity, and use this dictionary to translate it into learning new things about strongly coupled quantum field theory. And then you can change the right-hand side and postulate that by changing the right-hand side, I'm defining a new left-hand side. So you can change the right-hand side of the duality and define this gauge theory. And these people used basically to study strongly coupled quantum field theory in applications to condensed matter, to quark gluon plasma, to holography, to quantum information, etc. So that's a direction where we use computations we can do in gravity easily to learn about computations like entanglement entropy and stuff that we would have a very hard time doing in gauge theory. A totally different way of thinking about AdS CFT would be the opposite as a definition of quantum gravity. I could say, I don't know how to do quantum gravity. It's too hard. I don't know how to study what happens when I have 3 strings interacting. I don't know what's the measure of superstring theory. That's a very hard question. So I don't care. I take n equals 4 super Young-Mills, and that's the definition of the string theory. Right? You want to know what's the energy of a string? Compute the energy of the spin chain. That's the definition. Right? You want to know what's the 3-point function of 3 strings? Compute the 3-point function of 3 local operators. That's the definition. And so that's useful. That has many great points. For example, unitarity is manifest, etc. So many things we control very well in quantum mechanics, right? And then we use it to define quantum gravity. So will information disappear if I send some stuff? No, I mean, it's quantum mechanics. I mean, things evolve unitary, right? Maybe it's very complicated to interpret in the bulk what's going on. But there are not going to be puzzles with information going away, etc. when you are doing quantum mechanics, right? So it's useful. A last point of view, I would call it a guide. In a sense that it's telling you the answers. It's telling you, look, you want to learn more about Young-Mills theory? Here is an example. At strong coupling, you should expect this. And vice versa, it tells you want to learn more about very strongly coupled strings. Look, according to the duality, it gives you this. So it gives you it tells you what results to expect, and then you can go and try to develop more powerful techniques to compute on both sides. Right? And so, of course, this isn't what I'm just saying is that this would make contact with things like integrability, etc. What I would call developing new tools for quantum fields and strings. So we would use the knowledge of this duality to guess, to predict what the behavior of things should be. And in this way, we will develop and improve our way of thinking and not do mistakes and not forget about some subtle issues. Okay? So let me give you now an example, moving at 2 o'clock to the check that we set. Okay? So now we conclude this general discussion and we are going to discuss a check. Okay. So the idea is that we want to identify a string and a spin chain state, try to compute the dimension of that string and that spin chain state, and ask whether they are the same. Now, there are infinitely many strings, there are infinitely many words you can make on the spin chain. How do we go about finding who is who? Well, there are things you can do. For example, this string, each string state will have some transformation under rotations of the sphere, which is a symmetry. So here, there is an SO6 rotation group. And each state has some charge according to the rotations of SO6. Well, but in n equals 4, we have precisely an SO6. And we have precisely charges according to the rotations of SO6. So we can match. You have an operator which has j units of rotation here. It must be an operator with j units of r charge rotation there. Do you agree? It's just the same rotation. Right? So here we have SO6, which are just the isometries of the sphere. And here we have SO6, which is just the R charge of this theory, the R symmetry of this sphere that rotates the various scalars. And so a state with R charge J is mapped to a state with R charge J. A string can also have rotation. It can rotate with respect to this sphere as d minus 2. But this sphere is the same sphere at the boundary here. And if you translate back to radial quantization, an operator that spins is an operator that has spin. So if the operator has spin S, it would be a state that rotates in this sphere with spin S, and it would be a string that rotates here with angular momentum s. Just again by matching the other charges on both sides. And so we could look for what is perhaps the simplest solution of string theory, the one that we learn in flat space. If you read the first chapter of Green-Schwarz-Schwitten in flat space, the simplest string solution, the solution that gave rise to the beginning of string theory, is this type of rotating strings. If you remember, this is how people wanted to think about mesons. Mesons were two endpoints, quark and antiquark, with some tube of energy, and they were just rotating. Right? This is the simplest string solution you can write. It's just a rod, it stretches and it rotates, and it does some movement like this, rotating like this. So this would be an example of a state. This would be called the folded string. Or if you want, we can add here some rotating folded string. So this, again, in flat space, if you semi-classically write the energies of the rotating folded string, you get this linear trajectory that the energy of the string is proportional to the spin, right? And this was what was fitting very well the mass of the mesons that gave rise to the beginning of string theory. It's more or less true that mesons at very large spin look like folded strings, indeed. Okay? You have heard this, right? This Fauci, Fauci. It's Fauci? Fauci plot, Chiu-Fauci plot with the points. So we could try to study this string. Let's look for operators that rotate in AdS. What about in the sphere? Let's say that they don't do much in the sphere. They are just rotating in AdS. Okay, here, there's nothing much. It's boring here. And let's try to describe this folded string in AdS and in the gauge theory. Okay? So let's first do it. Let's first think about this operator. So our goal is to describe the simplest possible string, the folded string. And to describe the analog, which would be the folded spin chain, if you want. Okay, what is the folded string? Well, we could start writing the action for the string. The action for the string in AdS, right, for this rotating string in AdS would be what? Would be the string tension, square root of lambda over 2 pi, integral d2x. What's AdS? AdS is an hyperboloid, so this is more or less like the sigma model we wrote before. Dn squared plus a Lagrange multiplier, I need a new name because I have lambda outside, mu times n squared minus 1, where this n squared is not a sphere, but there is a few signs, it's an hyperboloid. So this would be the action you would study here. You agree? It's one way of writing. There are other ways. You could use another representation of AdS. And then in this string, you would write this. This is one way of writing the action. You could also write as square root of lambda over 2 pi integral of g mu nu in global coordinates del x mu del x nu. I just wrote here in embedding. You could write in global coordinates. And then in global coordinates, maybe that's a bit easier, you would have the cylinder. And then you would look for the solutions that describe this rotating rod. Let's just be a little bit more precise. Remember that we had this coordinate, rho. We had this rotating coordinate, let's call it phi. Let's say that everything happens here. And we had this time t. So we would look for solutions of our string that would be something like this. Phi would rotate, omega times time. T will just happily move, so it's a rotating object. And then this rho would have some non-trivial profile f of sigma. So this will tell you that as the string moves, right, as you move along sigma, you are moving here. and then you are rotating as a constant pi and t are just rotating as a rod. So you would plug this and that into this action, get some action for this function f, solve it, and compute the energy, and you would get that the energy is equal to square root lambda over pi times logarithm of the angular momentum by which it rotates, spin at large spin. In other words, the interpretation is that the string effectively, because it rotates, it becomes big because of centripetal force, right? It's rotating, so it's becoming big. There is some size that is effectively like log s, morally speaking. There is some tension, and this is the tension times the effective size of the string. It's telling that by this centripetal force, the string grows. It's not just centripetal force. There is the centripetal force that wants to increase the size, and there is the fact that it's in a box that wants to not to increase. So there is this competition between the centripetal energy of the folded string and the gravitational potential that keeps particles in a box. And it turns out that because of this competition, what you get is that the energy is proportional to logarithm of the spin.
Sorry, S is the spin of the string.
S is the spin. S is the spin or angular momentum. Now, this by itself is already a very nice result, as I'm going to tell you, because a priori, it could have been any dependence with spin, but being a number times logarithm of the spin is what you could generally argue that must happen in any conformal gauge theory at large spin. So there are theorems that say that if you have spinning operators at large spin, they should have this logarithmic scaling. But there was no way of computing the prefactor at strong coupling, and here we did it. It's square root of lambda over pi. So this is already quite a remarkable result that we could compute this. But okay, let's get there in a second. Let's discuss what could be the counterpart of that. It's a spin chain that has lots of spin. Now here, this part is AdS. I did not even worry about the sphere because the sphere was boring. There was almost nothing moving on the sphere. So I ignored the sphere completely and I just studied the classical motion in AdS. Right? That would be fine. It's like saying I have a rod rotating here and exploring this two plane and time, and nothing is happening in the other directions. I ignore the other directions. Okay? Okay, good. Now, what could be the spin chain? So we need an operator with lots of spin and the minimum amount of arc charge. Very little arc charge if possible. So an operator that does the job, our folded string operator, could be the following. I could draw a spin chain. I could think of a spin chain that has just two fields. Let's suppose we put two scalars only. One scalar is bad because if the theory is SUN, just one scalar, the trace would be 0. So let's put the minimum, it will be 2. And now, this operator is a scalar right now. So how do we give it spin? Derivatives. Now we can, instead of this, we can put many derivatives here to the k and many derivatives here to the n, where n plus k is the spin. Now, this is an operator, but this is a random operator. It comes with some wave function, psi n comma k. And this is what our operator is. And what fixes this wave function? This, I think here as a cat, which is n k, a spin chain state. What fixes the wave function? What fixes the state in the spin chain? Sorry? What tells you what combination of states to take on the spin chain? It was what we saw in the lectures. How did we find which linear combinations of states to take in SO6? What were the good primaries, the good bases of primaries?
The one that diagonalized edge?
The ones that diagonalize the Hamiltonian. So now we have a dilatation operator, right? And we want to take these operators. We want to take this to diagonalize the spin chain Hamiltonian. Now, this spin chain Hamiltonian is a new Hamiltonian. It's the one that acts on this funny spin chain, where at each site I have an integer 0, 1, 2, etc. I did not write this one. I wrote the scalar one, the one that acts on scalars and just permutes, etc. But we wrote a general one that acts on anything, right? And so by knowing how to act on anything, and we know what these guys are in terms of oscillators, we can deduce what this sector does. So these would be operators that if S is large, if S is much bigger than 1, they have huge spin and negligible R charge. Right? They have 2 units of R charge and 1,000,000 spin. Right? It's like saying the Earth, it has spin. Okay, it might have some deficit of maybe 1 or 2 units of charge, but it's irrelevant. Right? The fact that you have these 2 scalars, it's really the way to think about this operator, this folded spin chain, is really that you have a folded thing, and these 2 folds here are like the 2 scalars Z. So they need to have something to attach. It's like the quarks of the mesons. So the derivatives need to act on something, so they need to have some endpoints, but these endpoints are playing no role. It is just, what's interesting is the rotating part of the string. And so now, what you can do is here, you can now compute the energy of this quantum spin chain. So what we find is the following. So on the string, let me summarize here. On the string, or more precisely, this is when lambda goes to infinity. So I'm doing just classical string theory. There is no quantum, right? It's just classical. We find that the energy is the string tension, which is very big, square root of lambda times pi, times logarithm of the spin. Now, in the gauge theory, in n equals 4, which is when lambda goes to 0, and we are doing just one loop computation, you will find in today's tutorial that the energy is lambda over pi, maybe there is a number here, 8 or something, times logarithm of the spin. Okay. And so what is this? Well, they're not the same, of course, but they don't need to be the same because these are very different regimes. What we are computing is a quantity that we could plot as function of the coupling. And this quantity is the following, is the energy divided by logarithm of the spin as the spin goes to infinity. This is a function f of lambda, which has a name, is called the cusp anomalous dimension. It's an interesting function in any gauge theory. This exists, this quantity. And what we see is that this function starts linearly here as lambda over pi. It goes to some square root here, square root lambda over pi. But then here in the middle, we don't know. So it's hard to do a check with the CFT. So we compute here, how could we know? Right? Okay, we can say it goes up, so it probably goes there. If it went down, it was hard, but that's not very satisfactory. So how could we do better? We could use integrability and all these techniques that I told you about that tell you how to correct and systematically improve. And so with integrability, you can compute this curve exactly. So with integrability, what you find is that this curve beautifully goes here and precisely goes here. So this would be what we would do if we had developed these integrable techniques. But to do it required a lot of work. There were lots of techniques that had to be developed. And it was only possible because we knew where we wanted to get and we knew where we started. It would have been impossible to do it without knowing. And people computed this, and then people worked a bit harder, and they found the one loop correction. And the one loop correction is something like log 2 over 3, something like that, times lambda to the 0, plus, and then there is something 1 over lambda times some number. And there was a lot of work in string theory computing this one loop correction around the classical solution. And then that had to match this first deviation from strong coupling. And then there was work computing the next correction here, lambda square over 8 over 4 pi cube, whatever. And then there was more and more work from both sides, and then integrability had to glue them together. So this was really giving you the theory. This theory was telling you where you want to go, and the other theory was telling you where you want to go from the opposite direction. And so you were learning not only about integrability, but about how to develop better tools at weak coupling and at strong coupling. Okay? And so this is the energy of this folded string. So the idea is that this gets some corrections. This also gets some corrections. And then they are just equal to each other, these functions. And these are just the endpoints of the expansion of the same function. So what quantity did we study? That we did a check. It was the ground state energy of this folded string. The energy of this folded string, we saw that this state becomes long when the spin goes to infinity. This size becomes effectively log of the spin. And so the energy of this object divided by logarithm of the spin, it's some kind of density, ground state energy density, and that's what this F is, some kind of ground state energy or this folded string. At strong coupling, it's the energy of a string. At finite coupling, it's the energy of the flux tube that connects this quark and antiquark. So the proper way of thinking about this at finite coupling is that there is some kind of flux tube between the two. That when you go to weak coupling, it's a bunch of gluons being exchanged. When you go to strong coupling, it's a classical string. And in the middle, it is what it is. It's some quantum flux tube. And that's what this curve describes. So since Kendrick is not here, I want to mention this was a beautiful check of the duality that works. And maybe we should end on this positive note. Yeah. Should I stop here, or should I tell you one more check related to? No, I think it's no. Okay, no. I need to tell you something. Okay, I need to tell you something cool that is a little bit a little bit more advanced. So this is I'm hesitating. I will lose some people, and I think this is a cool positive point to stop. I was just going to tell you the punchline of what I was going to end. I was going to say we could study fluctuations of this folded string, the quantum analysis of this folded string. And what would we see for the quantum, this model of the folded string? We would see that the string is rotating in AdS and doing almost nothing in the sphere. Right? Now, doing almost nothing in the sphere means what? Means that the sphere could be pointing in any direction, and it costs no energy to do something else. So you could imagine that there would be what? There would be some rotating string in AdS, and then nothing in the sphere, so a bunch of massless modes that will tell you where you are on the sphere. But we know this is not true. We studied the model of the particle on a string, on a sphere. And we saw that there is quantum dynamical mass transmutation, and actually these particles acquire a very small mass. And so, in fact, the same physics of this folded string would make contact with the description of the sphere sigma model that we described with n equal to 6 here. Because the sphere is almost empty, so there's almost nothing in the sphere. But these strings that are in the sphere, they cannot just be massless. They must acquire this mass and be very, very light. They are Goldstone particles wannabe, but they are not Goldstone particles. And this will tell you that you must reorganize the degrees of freedom. If you do an expansion at strong coupling, the naive one, you get a bunch of massless modes and a bunch of massive modes. But quantum mechanically, you need to reorganize them, and you need to have, instead of 5 modes here, you need to have 6 modes here. And then instead of 3 modes here, you will need to have 2 modes here. And what will happen when you do this is that you would think that you have all the modes to describe the sphere. But some modes that you needed to describe AdS, it looks like it's disappearing. There is one mode of the string that naively disappears. And you could think, is this a bad thing? Is this a good thing? You could say it's a good thing because there was, from the point of view of the boundary, there is no extra dimension. There's only the boundary. But on the other hand, I do want this extra dimension because I want AdS. So what would be the best case scenario? The best case scenario is that there is no holographic direction. But when you go to strong coupling, this direction emerges. When you go to string theory, when you go to strong coupling, then you see a classical dimension emerging. And that's precisely what happens. What happens is that at finite coupling, you have a bunch of excitations, scalars here, gluon excitations here, and there are fermions on the superstring. And what happens at strong coupling is that these fermions form a bound state, like a Cooper pair, and it's the bound state of the 2 fermions that only at strong coupling form a classical bound state, and they give the extra holographic direction needed to describe AdS. That's an example of a super cool phenomena that I think, without knowing what exactly we wanted, without knowing that string theory wants this extra dimension and you want this extra mode, we would never have found this phenomena of binding and forming these Cooper pairs and the fermions of the flex tube confined to give an extra holographic direction and so on, which is really a truly awesome physics piece. So this, I think, would be a very great point to illustrate how AdS CFT can be used not only to define quantum gravity, to define gauge theory, but to really guide us and help us discover some amazing new physics. So I think let's stop here. Okay. Thank you. It's a gift?
It's a gift.
Oh,
And then
thank you.
there's something on the, like if say a few throughout the class, I just keep ascending. I keep ascending, and then that's where I end up with B.
Oh, very nice. Okay. Cool. There you go. Okay, thank you. Very good. Good size, yeah. Okay. Very good. Yeah, it will be great. I need to add some cartoon here, but almost perfect, yeah. Thank you.
Next time we'll do a cartoon.
Yeah.